What we assume is what I've come to call an impulse drive on the verge of being able to ascend an incline of 2 degrees. The basic way this device works is that we have a ball bearing being accelerated around a specially shaped track. The track has 2 curves, which when traversed by the ball bearing create centrifugal forces. The small curve creates a large force that acts on the track and ball for a short period of time. The large curve creates a comparatively smaller force that acts on the track and ball for a comparatively longer period of time. Also, there is another force acting on the track and ball at some point between these 2 curves, which is how the ball is actually being accelerated around the track. And the sign of this additional force depends on which way the ball is circulating around the track. The momentum of the track that is produced by these forces oscillates, but it does so asymmetrically, which means it can have an average value in different directions, and for the x momentum will look something like the graph on the left. If we integrate this x velocity over time, look at the graph on the right, which has a net displacement. This analysis is not yet subject to the effects of a constant outside body force like gravity. It's assuming the device is just oscillating its way across flat, frictionless ground. The fact that our system's momentum oscillates is actually irrelevant with regards to whether or not it can displace against a constant outside body force like gravity, as long as the system's momentum does in fact have an average value. The only relevant question as to whether or not a system with an average momentum can overcome gravity is if we are adding energy into that system at a rate that is faster than gravity is taking energy out of that system. Just look at this graph of force over time. The flat line is gravity, and we're forcing the system with periodic impulses by accelerating the ball with an electric motor attached to the track. In order to have our system displace against gravity, all we need to do is make sure that the total area of these impulses is greater than or equal to the total area of the flat graph of gravity over an equal timescale, which just means that depending on how far apart in time our impulses are spaced, they'll have a corresponding minimum amplitude necessary for the system to displace against gravity. In the past, I've created different simulations of the device by trying to derive and discretize differential equations that describe the forces that the ball and the track create on each other throughout time. For example, if we have this red ball bearing accelerate to the right as it traverses the large curve, a centrifugal force will be created and cause the track to accelerate towards the right, which will cause the speed of the ball bearing to decrease. Because the ball can cause its own path to displace, we have to be very careful about how we define coordinate systems when deriving math to describe such systems. For example, if the track were instead to accelerate to the left, the ball would stay still from our perspective, but it would still traverse the curve and create a centrifugal force, which in this case would cause the track to deaccelerate and the ball to accelerate. So if we want to describe the centrifugal force that is created in terms of the ball's tangential velocity, we have to define this tangential velocity as being the magnitude of the difference between the velocity of the ball and the velocity of the track. By examining the forces created from the ball traversing the curves of the track and applying the constraint of conservation of energy to the system, we can create very complicated differential equations that can be discretized to simulate the motion of the ball on the track. But this method is difficult, and I've recently discovered a special trick to make the process a lot faster and easier. As the ball traverses the track, its momentum's direction will rotate. In order for the ball's momentum to rotate, a force must act on it. This force will act equally and oppositely on the ball and the track. We apply conservation of momentum and energy to the difference between discrete points on the track, but we at the same time can make this computation easier and solve for fewer variables if we use the fact that since the ball is constrained by the track, as long as the magnitude of its momentum doesn't change sign, we already know which direction the momentum of the ball will have at every point in the future, just not its magnitude. So from a starting point, with known initial conditions, we can have a discretized form of conservation of momentum and energy equations iteratively reach forward in time to solve for the next position's corresponding ball and track momentum. This simple system is actually pretty complicated. Different sections of the track here are color-coded and matched to the track's x velocity, the ball's x velocity, and the track's displacement in the x direction against gravity acting in the positive x direction. Red arrows are the ball's velocity at different points along the track, blue are the track's velocity, And we can see that this device does in fact satisfy conservation of momentum and energy, and still displaces itself even against gravity. This is the same simulation continued for additional circulations of the ball around the track. There's a small but definite average velocity of the track against gravity, which in this simulation is defined to act in the positive x direction. This device can be improved upon by introducing a spiral into the track, which also goes through a rotation. If we look at this picture as an example, we can see that the negative of the derivative of the tangent vector's x component produces a reaction force in the same direction on either side of the spiraling curve. This means that, for example, by making the track spiral around the small curve, we can add in 2 additional reaction forces that will accelerate the track towards the small curve. The centrifugal force from the now spiraling small curve will still be present and produce a net value, but it will oscillate due to the curve's spiral. This doesn't really matter though, because the magnitude of the reaction forces created by mass entering and exiting the spiraling section of the track is dependent upon the rate at which the track spirals outward, which is essentially a free variable, as it is only limited by the physical geometry of the mass traversing the track.
So this is all neat, but what is it actually useful for? Well, potentially a lot of stuff, but this depends on 2 things. The first is whether or not this can be generalized to some other system that is more useful than a revolving ball bearing. In its simplest components, all the system does is constrain momentum to exist on a specially shaped track, which means we should be able to generalize it to any system that carries momentum, like a flowing fluid, or even electromagnetic waves. Exactly how, though, I haven't quite figured out yet. The second is whether or not this system can scale. If we wanted to use it as an actual drive system for a machine, we needed to produce a lot more force a lot faster. What if we could accomplish both of these things? Well, then it allows us to create aircraft that are capable of atmospheric as well as spaceflight. There's not really anything stopping us from pointing the system up rather than horizontal. And if it creates enough force fast enough, it should be able to overcome gravity, allowing us to create aircraft that fly without the need to displace air in such a way as to create lift or thrust, which means they can fly just as easily in vacuum as atmosphere. This, for example, could drastically reduce the cost of spaceflight. You could put objects into a different kind of orbit where instead of giving them enough kinetic energy that they effectively fall over the curvature of the Earth, they hold themselves in place at a specific altitude as long as they have enough energy storage. If they have big enough solar panels, they could hold themselves in place indefinitely. Tetronics is an alternative theory of quantum mechanics that was created by Kelvin Abraham, an electrical engineer from Australia, and it was published in a mostly complete form online way back in 2012. It's a reformulation of quantum mechanics and basically all physics in terms of geometry. By making a few assumptions about what energy is and following these assumptions to their logical conclusion, we can, among other amazing things, derive the periodic table of the elements and its properties. Tetronics has several issues and is not a complete theory. One of its issues is its own scope, as it redefines absolutely everything in physics in terms of geometry, making it hard to talk about if you don't have a working knowledge of what it is and how it does what it does. So for the next hour or so, I'm going to give you a quick crash course in Tetronics, and then at the end we're going to come back to what impulse drive has to do with theory. It's a long walk, but I think the destination is well worth it. What we're looking at here is what we assume energy to be. Tetronics energy is made out of equilateral triangular coins. We call them quantas of energy. It's comprised of 4 different field components. The light blue and green are magnetic fields. The red is a positive electric field. The dark blue is a negative electric field. Each one of these triangles here is one side of an energy quanta. These energy quanta are perfectly self-inductive, so the electric fields create the magnetic fields create the electric fields. There's some mathematical wizardry that we'll talk about more later. They distribute themselves through space in the shape of this geometry. We use these quanta to describe everything in physics, so in order to describe the energies of motion of things like particles, these quanta need to have a velocity associated with them. So we do associate a velocity with one of these quanta. It's a velocity vector that points from the base of the quanta to its tip, and these quanta, when unconstrained, will travel through space according to their velocity vectors. Now, like I said before, we'll come back to what all this has to do with the impulse drive later, but already you might be able to see a bit of what's going on with regards to these cycling fields and their velocities. To describe velocities higher than one quanta's worth, we join quanta together to create a larger equilateral triangle out of them. By growing this energy geometry in odd-numbered jumps of additional quanta, we can get one extra unit of net velocity to the entire geometry for every row that we add. We restrict quanta in T-theory to only be able to join together in this pattern, and this is the way that we reformulate quantization in T-theory. Something interesting to note with this reformulation is that under it, quantization actually occurs continuously, which sounds like an oxymoron, but let's say we decrease the amount of velocity associated with each one of our quanta. This allows us to increase the amount of total quanta within this energy geometry without changing its net behavior. So we can see that in T-theory, quantization is a geometric constraint. Everything has to come in equilateral triangular chunks. In order to describe the kinetic energy of things like particles, these quanta also need to be able to describe mass. Here we have Einstein's famous equation, which we will alter our interpretation of slightly. We're going to say that what the speed of light squared is physically describing is the value of a second-order time rate of change in the area that our quanta occupy in a reference plane. And what I mean by that is that if we have the quanta rotate and we pick some reference plane, for example the white triangle in the animation, over time we have a varying amount of the quanta's area projected into that reference plane. So the amount of energy quanta within this changing area within our arbitrary reference plane is what we define mass to be. Making our quanta rotate gives us two different types of them. Quanta that rotate according to a right-hand rule, where your thumb points in the direction of the quanta's velocity, and your fingers curl in the direction of the quanta's rotation, and quanta that rotate according to a left-hand rule. Quanta now have two different polarities that join together to form larger energy geometries, such that the larger geometry has the same sign of polarity. For example, if we have a geometry with two rows and the outer three quanta are right-hand rule quanta, then the interior quanta is a left-hand rule quanta. This means that the entire geometry will rotate according to the right-hand rule. A simple exercise to see why is to place your hands together such that your thumbs point in opposite directions and curl your fingers. They both curl in the same direction from any point of view. Now we're going to use the geometries we've constructed so far to redefine quantum uncertainty. This is where things start to get very interesting with T-theory because so far, since we're using a discrete geometry to describe energy, the theory is completely deterministic. And yet, you'll see it can also recreate uncertainty. We've defined energy geometries to only grow or decrease in odd-numbered jumps. If we compare the jump between energy levels of a geometry that is small and has few total quanta to one that is large, obviously the gaps in energy are different for each geometry's next jump. Our quanta have mass and velocity associated with them, so they describe momentum. The change in momentum of each of these geometries is different because of geometric quantization. The gap in momentum for the small geometry is small, and the gap in the large geometry is large, so we can basically satisfy the uncertainty principle for momentum and position by associating wavelength contraction with our energy geometries. You'll notice our geometries are made out of repeating units, so we define their frequency to be the number of repeating units moving past a point per second, and their wavelength is of course the physical length of these repeating diamond units. So we require that as geometries grow in number of quanta, they shrink, meaning the gap in wavelength for larger geometry is small compared to the gap in wavelength for the smaller geometry. This also requires us to reinterpret what the uncertainty relation is physically describing to literally be two differential units of measurement that are inversely proportional to each other. Now you might wonder, what basis do we have for assuming that the quanta wavelength contract? Let's think back to the impulse drive for a moment. We have the track displace each time the mass traverses it. More cycles per second means a greater average velocity of the track. One way we can get more cycles per second is to reduce the length of the track, making the track smaller and the ball bearing smaller and denser. So we are potentially seeing now some of the forest through the trees with regards to how the impulse drive relates to all this, but we'll talk more about that later. We can use the same argument for the other uncertainty relationship between time and energy. For small geometries, the gap in energy for successive jumps is small and is large for large geometries, which means that to satisfy this uncertainty relation, the quanta also have to have the property of time dilation. We define the quanta to have mass and rotate. If we further assume that the force that is causing them to rotate is a single magnitude that doesn't change, it means that larger geometries with more mass must rotate slower because they have greater rotational inertia, thus creating time dilation. Once again, we have to alter our understanding of what we're physically talking about, though. We have that quanta rotate. In order to interact and create forces, they have to overlap in the same space, which requires them to be in the same reference plane. So we can think of this delta t as being associated with the amount of complete rotations an energy geometry accumulates relative to some arbitrary reference time. We're just counting how fast our clock is ticking. Pretty soon we'll know enough that we can start to actually construct matter, but first we need to define how Tetrayonics models electric and magnetic forces and photons. By placing two larger energy geometries, which from now on we'll call chem fields, KEM for kinetic electromagnetic field, we take two chem fields of the same net polarity and stick them back to back via their magnetic field components. We now have these big diamond geometries, which is all one polarity. The same polarity of whatever quanta is on its outer edge. On the left, we have two right-hand rule quantas, or right-hand rule chem fields stuck back to back. Their curls cancel each other out, and the geometry has no net curl. It's static. It also doesn't propagate through space. Since it's stuck together via opposite polarity magnetic fields, it has no net magnetic field, though it's still partially constructed out of magnetic fields. This is how we create an electrostatic field in T-theory. When electrostatic fields overlap, their quanta interact to create a force. This force follows the law of interaction. Likes repel, opposites attract. Without getting into the inner workings of how these electric and magnetic fields induce each other, which we'll do more of later after we come back to the impulse drive, there's not much to explain here, other than that we assume that opposite polarities of fields attract each other and similar polarities repel. We can do the same thing for magnetostatic fields. By sticking together a left-hand rule and a right-hand rule chem field back to back, we get a diamond geometry stuck together via its electric field components that has a net magnetic field and no net electric field. Where once again, we assume that when the quanta overlap, they create forces according to the law of interaction. Opposites attract and similars repel.
We use this same geometry to describe photons, the discrete packets of energy that superposition to form electromagnetic waves. The difference between magnetostatic field geometries and photons is that photons propagate, in this case, out of the screen towards you. We can construct electromagnetic waves out of photons by stacking them on top of each other, varying the total energy content of them across the stack, as well as the relative orientation of their cancelled charge components. Then have this stack propagate through space. At this point, you may be wondering, if this reformulation of physics is true, why are waveforms not measured to be more triangular? The answer is simple and is related to Fourier analysis. Here we see a photon with its charge components highlighted. The geometry rotates. We'll assume according to a right-hand rule with our thumb pointing up. It also propagates out of the screen. If it propagates much faster than it rotates, we can imagine a scenario where we can view it edge-on as it comes towards us, or equivalently, that the geometry is just moving to the left across the screen. The geometry is constructed from repeating diamond subunits. Each plus-minus pair we equate to being a single unit of electric field. Then, as the geometry moves to the left, we equate the strength of the electric field as being the number of plus-minus pairs stacked on top of each other like batteries in series. We also take the number of repeating plus-minus diamond pairs passing by us per second to be the frequency of the photon. Let's imagine what will happen in the hypothetical scenario where we increase the speed at which the geometry passes by us. If the geometry's speed increases, the width of its triangular signal decreases. Because we measure more frequency units per time, its amplitude also increases. We know this due to Planck's relation here. the energy of a photon is proportional to its frequency. The total energy in this case is the same, but the concentration of the energy in time corresponds to an increase in the signal's measured magnitude. Continuing this process results in the graphical method of defining the hypothetical impulse function, a function of zero width, infinite height, and a total area of 1. Using Fourier analysis and the sampling theorem, we know that we can digitally reconstruct any signal as the weighted sum of time-delayed impulse functions, which means that if our energy quanta are small enough, move and cycle fast enough, while they are discrete in nature, they can create the illusion of being continuous. This effect is compounded by the finite reaction times of real systems due to their inductive and capacitive components. Here we have 4 special tessellations of our quanta that, as depicted, are unstable and cannot exist. However, if we fold them into 3D tetrahedral geometries, they will be stable and can exist. These form particles called tetrons and are the building blocks of quarks. They're held together by the law of interaction acting between the magnetic and charge components of the quanta. The top left tetron has a net positive charge as all of its 4 faces are red. The top right is negative because all its 4 faces are blue. The 2 bottom tetrons are neutral as they have an equal number of red and blue faces. We take one negative tetron and 2 bottom left neutral tetrons and join their oppositely colored faces according to the law of interaction, we will create a down quark. If we take 2 positive tetrons and 1 bottom right neutral tetron and join their oppositely colored faces according to the law of interaction, we will create an up quark. By joining a down quark, an up quark, and a down quark according to the law of interaction, we will form a neutron. A neutron has no net charge, as of its total 36 faces, half are positive and the other half are negative. We can form a proton by joining the oppositely colored faces of an up quark, a down quark, and an up quark. A proton has a net charge, as of its 36 total faces, 24 are positive and 12 are negative. By once again simply following the law of interaction, we can join a neutron, a proton, and an electron to form a deuterium atom. An electron is formed by magnetically joining 3 negative tetrons around a common axis. It has 12 negative faces, giving it the same net charge as the proton. The deuterium atom behaves like an induction motor, with the nucleus taking the role of the stator and the electron the rotor. The electron is induced to spin by the oscillating acceleration fields of the quanta, signified here by rotation. We must remember that these quanta are simplified depictions of the essential elements of the geometries of an n-particle system.
Furthermore, there are actually far more quanta per phase on these geometries than depicted. By following the law of interaction, we can use the deuterium atom as a building block to construct the rest of the periodic table. Each electron spins in the same direction relative to its nucleus, but to join these two nuclei together, we had to flip the orientation of one of them, so that from this perspective, each electron is spinning in opposite directions. The spin of electrons is not thought to be a literal physical rotation in the Standard Model. We will justify the interpretation that it is later. For now, we just continue to follow the law of interaction, building up and out symmetrically, coincidentally reconstructing the same progression of orbitals as is in the Standard Model. Let's skip the rest of this tedious process and take a look at the end result, the periodic table 2.0. At the bottom right, we see a side view. Each row is a separate quantum level comprised of different orbitals. On the first, we have S1 and S2. On the second, S1, S2, and P 1 through 6. On the third, S, P, and D. On the fourth, S, P, D, and F, the top half being a mirror image of the bottom. As I previously stated, the orbitals are filled up and out according to the same pattern as the Standard Model. The central figure is a slice of the fourth or fifth quantum level viewed from above. Here's the S1 and S2 orbitals. P 1 through 6, D 1 through 10, and F 1 through 14. There's one huge difference between this periodic table and the Standard Model, and that is that the ratio of neutrons to protons is 1 to 1. In the Standard Model, stable atoms have a ratio of approximately 1.5. This is because in this formulation, neutrons have varying amounts of rest mass in their matter geometries. The neutrons in higher quantum levels have more mass matter than the neutrons in the lower quantum levels. This reformulation still satisfies the experimental observables relating to neutral particle detection because neutral particles cannot actually be detected, but are deduced to exist via applying the principle of conservation of momentum.
The rest mass of the neutron in the nucleus determines the base rate of spin of its corresponding electron. The spin of electrons in this reformulation is a literal physical rotation. Electrons have a tiny measurable magnetic field. Charges in motion produce magnetic fields, but in the Standard Model, the intrinsic magnetic moment of an electron is not thought to be caused by actual rotation of charge. This is because, in order to have the necessary amount of quantized angular momentum, the electron would have to spin faster than the speed of light, and it is not possible for matter to travel faster than the speed of light in the Standard Model. In this theory, things are reversed. Quantized angular momentum, specifically as opposed to general angular momentum, is not associated with the rotation of matter, but more generally with the intrinsic rotations of the particles that create our energy quanta. Thus, rotating electrons possess the necessary quantized angular momentum without spinning faster than light speed. The triangular geometries that describe the kinetic energies of matter in motion also possess magnetic moments. Each electron has such a geometry to describe its tangential rotational velocity. The energy of this geometry also describes the energy state of the electron. As I stated before, each deuterium atom acts like an induction motor. Photons can induce the electrons to spin faster, but in order to do so, they must be absorbed into the tangential kinetic energy geometry of the electrons. An imbalance of kinetic energy between the electrons of an atom drive the emission process. We observed before that to join nuclei together we had to alternate the orientation and subsequently the direction of rotation of the electrons, coincidentally satisfying the Pauli exclusion principle. For simplicity, we imagine the electrons to be revolving point masses. If two such point masses revolve in the same direction and speed, the center of their mass will revolve in a circle with them as the central point between them. In contrast, if the 2 point masses revolve in opposite directions, their center of mass will only bounce up and down, the horizontal component of its oscillation being cancelled. This makes the system more stable. It can be made even more stable through the addition of more revolving point masses with different phases, cancelling out the vertical oscillations of the system's center of mass as well. If, however, one point mass was to revolve at a greater speed, the system's center of mass will begin to oscillate more chaotically. In the Standard Model, the oscillation of charges emits electromagnetic radiation. The same is true in this reformulation of physics. The imbalance of rotational kinetic energy between electrons creates instability and drives the process of emission of that excess energy as a photon. We will soon see that the energy content of these kinetic electromagnetic, or chem field geometries, changes their rate of rotation. Thus, the difference in mass-matter content of the neutrons at the top and bottom of the periodic table also induce instability, and this is the driving factor for radioactivity. You may be wondering, if this theory is correct, why have tetrons not been discovered in particle collider experiments? To understand the answer, we must first learn a bit about how the detection of particles works in such experiments. Particles are detected via the photoelectric effect. If a charged particle impacts a charged plate, it will knock electrons off the plate. In a photomultiplier tube, those electrons then impact another charged plate, knocking off more electrons. This process continues throughout the photomultiplier until a measurable pulse of current is created and recorded as a measurement of the original particle's position. Particle detectors consist of a vast array of such devices, allowing for the tracking of the path of a charged subatomic particle through them. Neutral particles cannot be detected in this way. They are inferred to exist by applying the principle of conservation of momentum to otherwise inexplicable changes in the trajectory of charged particles. A particle collider generally collides two oppositely traveling beams of charged particles at the center of a detector. The particles, in theory, explode into their subcomponents that then travel through the detector and are categorized. The process usually occurs too quickly to produce useful data, so the speed of the particle wreckage is slowed down by scintillator material, and a powerful magnetic field. Charged particles moving through a magnetic field will be acted upon by a magnetic force, causing them to travel in arcs. The greater a particle's charge and velocity, the stronger the magnetic force will be and the greater curvature its subsequent path will have. The more mass and velocity a particle has, the greater its inertia will be, and the less curved its path will be. Thus, supposedly unique particles are categorized by their charge-to-mass ratio. By coincidence, tetrons have the same total fraction of an elementary charge as quarks. Furthermore, the mass term in momentum should include both the mass matter of a particle and the inertial mass of a particle's chem field. Thus, through equal charge and variable total mass content, many particles are indistinguishable from each other using this classification scheme, and many supposedly unique particles of the particle zoo are redundant.
So this is all the basics of T-theory. We can also go into how it describes gravity, which it does, but that would take too long. Now I'd like to talk about how the electric and magnetic fields induce each other and create the quantized velocity, and how this is all related to the impulse drive. So far, T-theory describes things qualitatively. I've been working for many years to create a mathematical model of the quanta that will allow the theory to make computational predictions. The model should describe how the electric and magnetic fields induce each other, how they create the quantized geometry, propagate that geometry through space, and how they join quanta to create larger geometries and forces. How this all works, I haven't completely figured out yet, so you might be wondering then, what is the point of all this if the theory isn't complete and we already have theories that work, especially since a lot of what we've created with T-theory here was based on some arbitrary assumptions about energy. But just look at how much mileage we got out of those assumptions. T-theory getting as much right as it does could all just be a coincidence, but how many coincidences do we need before we start to suspect a pattern? I think it's more likely that instead of it being a coincidence, the geometries work out this way because this is the way the universe actually is. So like I said, I don't have a complete mathematical model, but I have many pieces of one, and I think I have a pretty good idea how the model should work. So maybe the best way to relate this is to just explain one by one some of the different iterations of ideas I have gone through so far for trying to model these quanta. The first important aspect of the model is that the electric and magnetic fields should induce each other. The way this works in classical physics is the electric and magnetic field time derivatives are related to each other through a curl operator. So what we need is the vector fields of the electric and magnetic fields that the quanta are comprised of to curl around each other like two perpendicular loops. We also obviously need that the electric and magnetic fields distribute themselves through space in a triangular shape. So we probably want one of the loops to bend such that it becomes triangular. By doing that, and distributing everything throughout 3D space, we get this conical geometry, where the electric field fountains out its tip, comes down the sides of the cone, then goes back up the central axis and up the tip again. The magnetic field curls around the cone's surface. There are many different ways to mathematically define conical fields like this. We could, for example, do something like this, but this has the problem that it defines the field to exist everywhere throughout space. And to really make the resulting field distribution triangular, we have to restrict it using an arbitrary logical condition, where here we say that this vector field isn't defined for negative z. Ideally, we would like the geometry of the quanta to be an emergent property of some kind of mathematical system, so that when we perform computations or run some kind of simulation, we aren't constantly carrying around a bunch of arbitrary logic statements. Otherwise, we would also have to figure out some way to alter those logical statements for cases where quanta transfer between geometries to create acceleration. Basically, arbitrarily defining the quanta's geometry means that every quanta has to always somehow keep track of what geometry it belongs to and why it belongs there. And trust me, we don't want to have to deal with that. One day I noticed that if we take 2-point particles as being the source of two oppositely curling vector fields, place them like so, and superposition the vector fields they create, we get this field distribution in the center at the bottom. It's roughly triangular, and we can restrict it to mostly only exist locally by having the strength of the vector fields emanating from the point particles decrease with distance from the particles very quickly. If we extend this to a 3D ring of point particles, we basically get the fountaining conical electric field that we hypothesize our 3D vector representation of the electric field should probably be. If we go back to a 2D vector field representation for a moment and view this ring of point particles from above and give each of them another circulating vector field perpendicular to the first, the superposition of the fields from all these particles roughly creates what we hypothesize the magnetic vector field should be. So this is good and interesting. We can simulate systems of concentric rings of particles that create two perpendicular curling vector fields, which rotate the direction of a velocity vector intrinsic to each particle, and those rings will leapfrog each other and roughly trace out conical geometries through space and time. But this model has the limitation that we cannot, or at least that I could not, figure out how to spatially isolate the vector field of each particle enough that we can join these concentric leapfrogging rings into larger geometries and have them keep their own individual geometry. Everything falls apart and it just creates this very large swirling mess of particles that has no distinguishable geometry. Let's take a detour to quickly examine the resonance modes of a vibrating metal plate in the shape of an equilateral triangle. Basically, this gives us the exact geometry we want, and we can use the solution of these resonance modes as a multiplication factor on any arbitrarily defined vector field's magnitude throughout space to force it to have the required geometry. But we assumed that this geometry via the boundary conditions on the differential equation for the vertical displacement of a plate. Once again, this geometry only exists because of arbitrary logic conditions that we assumed, which is what we don't want to have to do. But this example of a mathematical system and the previous concentric ring model do both tell us something useful. The plate model periodically recreates its own boundary condition. The particle model preserves the initial structure of the concentric rings. It is possible that whatever mathematical system we use to describe quanta doesn't have to have the geometry be an emergent property of it. It could just be its assumed initial condition, and what we require is the system to preserve the geometry of those initial conditions over time and through interactions of separate geometries. So the state of things regarding modeling the electric and magnetic fields of the quanta and how they induce each other is not very good. We basically just know that what we want is some kind of system of differential equations, probably involving a curl operator, that the triangular geometry of the quanta is an emergent property of, or else the system preserves this geometry as an assumed initial condition through time and interactions of separate geometries. Let's change gears now and talk about how the electric and magnetic fields create the quanta's velocity. One day I noticed this interesting fact. If we take an equilateral triangle, split it in half into two 30, 60, 90 degree triangles, and assume that we somehow apply a force of equal magnitude onto every side of the 30, 60, 90 degree triangles, and then we decompose these forces into their x and y components, what we find is that the x components all cancel, but there is technically a net y component on the entire structure, though it is small. This is a strange property of geometry that I'm pretty sure, though I have no actual proof, is unique to triangles, or at the very least, triangular geometries. So by projecting a force along every side of a triangle and pairing it with another, we can have a loop of force that creates a net force on the overall larger triangle. But because it's currently defined as a force, it should just continually accelerate the triangle faster and faster and not conserve energy. So while this is an interesting fact about triangles, it's missing a component to make it realistic in describing how tetrayonic quanta work. The component that I one day came to believe is missing is time-varying oscillations. If we were to assume that we have two wells of energy, which together comprise all the energy of the quantum, where one well is full of linear kinetic energy and the other is full of rotational kinetic energy, then we can have the energy oscillate between filling these two wells in such a way that we can have the geometry move forward and rotate it at the same time and conserve energy. We assume that in the center of the vertical linear portion of the 30, 60, 90 degree triangles, we have maximum linear kinetic energy. And down at the edge of the base of the larger triangle, we have maximum rotational kinetic energy. And this energy is carried along these triangles by some kind of particle with mass. We can see that as the particles traverse the triangular track, their distance from the central axis changes, which changes their moment of inertia about that axis, and subsequently their rotational kinetic energy. Then we just need them to rotate around that axis at varying speed, traverse the triangular track at varying speed, and have them somehow interact with this track such that they trade energy back and forth with it. Like, for example, they give it linear kinetic energy in the form of an impulse, and it passes the energy back as rotational kinetic energy. Then what we have is a system of mutually inductive oscillating energy that can displace itself as a result of those oscillations. In this model, the fountaining electric field would correspond to the track itself and its linear kinetic energy, and the rotating magnetic field would correspond to the rotational kinetic energy. As we previously saw, by just having point particles create two perpendicular curling vector fields, associating an intrinsic velocity vector to these particles, whose direction is rotated by the superposition of these vector fields without having its magnitude change, we can start with concentric rings of these particles, and they basically do what we want. The issue is that I don't know how to take this structure beyond a single quanta without that structure falling apart. This kind of strategy is basically a Monte Carlo kind of simulation technique where we are simulating the behavior of control masses. Though once again I don't know how, there should be a way to extend this to a control volume model or a continuum model by letting the number of particles go to infinity. So this is the state of making Tektryonics computational. Pretty sure I know how it's supposed to work, but I haven't been able to find the actual system of differential equations that will allow it to. It's like we have a solution that is looking for the problem that it solves. T-theory is interesting because it conceptually simplifies a lot of physics by redefining things in terms of geometry and changing our physical understanding of what certain quantities mean. But more than that, to be a useful scientific theory, it should make predictions that are testable and more, hopefully useful for something. In T-theory, quantization is continuous and chem fields are fractal. This means if T-theory is true, we should be able to make a macroscopic chem field or analog of one that has all of its useful properties. The most useful one being its associated velocity, because it would allow us to make aircraft that fly without the need to displace air or to create lift or thrust. This is where we come back to the impulse drive. The impulse drive is basically a 2D version of a 3D quanta. Through the traversal of a mass along a triangular track, we can have that track displace itself.